Imagine the planet's mightiest oceanic highway suddenly deciding to reroute itself. Could that spell disaster or transformation for life on Earth? That's the startling possibility looming over our oceans today, as groundbreaking research hints that the Antarctic Circumpolar Current, the largest and most powerful sea current on the planet, might relocate over the next few hundred to thousand years. This colossal shift could fundamentally alter global climates and ecosystems in ways we're only beginning to comprehend. But here's where it gets controversial. While some scientists see this as a natural cycle exacerbated by human-induced warming, others debate whether we're accelerating a process that could lead to irreversible ecological upheaval. And this is the part most people miss. Understanding how this current has behaved in the past might be our best clue to predicting a turbulent future. Let's dive in and unpack it all step by step. So even if you're new to ocean dynamics, you'll feel like a pro by the end. At the heart of this story is the Antarctic Circumpolar Current, ACC, a massive, frigid waterway of seawater that circles clockwise from west to east around the continent of Antarctica. Picture it as a never-ending river of cold water, propelled primarily by the relentless southern westerly winds. These winds blow freely around the southernmost landmass because there are no large continents in the way to block them, allowing the ACC to maintain its strength and steady flow. For beginners wondering why this matters, think of the ACC as a vital connector in our planet's water world. It serves as a crucial bridge linking the Atlantic, Pacific, and Indian Oceans. This means it plays a starring role in transporting heat around the globe, influencing the carbon cycle that helps regulate our atmosphere, and distributing essential nutrients that support marine life in the oceans. Historically, scientists once viewed the ACC as a rock-solid, unchanging force of nature. But recent studies are flipping that assumption on its head, revealing that this current has a dynamic history that's anything but static. To uncover its secrets, an international group of researchers turned to deep-sea detective work, analyzing core samples drilled from depths of 3,000 to 4,000 meters. That's about 9,800 to 13,100 feet beneath the surface of the Scotia Sea, located just north of Antarctica. These long cores, sometimes stretching hundreds of meters, act like time capsules, preserving layers of sediment that tell the tale of the current's past behavior. One clever tool in their investigation is grain size analysis, a method that might sound technical, but it's really quite straightforward. When the ACC flows swiftly, it picks up and carries tiny particles along for the ride. These fine grains only settle to the ocean floor when the water slows down. By measuring the size and distribution of these particles in the cores, scientists can reconstruct how fast the current was moving at different points in history. It's like reading the rings of a tree, but underwater and focused on speed instead of age. And what did they discover? In warm periods from Earth's past, the ACC ramped up its speed dramatically. To give you a sense of the scale, Dr. Michael Weber from the University of Bonn Institute of Geosciences shared that during the second-to-last warm period, about 130,000 years ago, the current's velocity was over 3 times faster than it has been in the recent millennia, including our current warm era. This surge in power wasn't random. The researchers link it to subtle changes in Earth's orbit around the Sun. These orbital shifts, occurring roughly every 100,000 years, tweak the amount of solar radiation reaching our planet, warming things up. Additionally, variations in Earth's axial tilt and rotation happen every 21,000 years, adding another layer of influence on global temperatures and, consequently, ocean currents. But the story doesn't stop at speed. It gets even more intriguing with location. During those ancient warm spells, the ACC didn't just accelerate, it also migrated southward, inching about 600 kilometers, roughly 372 miles, closer to Antarctica itself. Weber explains that this shift pulled warmer waters nearer to the Antarctic ice sheets, which could have played a role in elevating sea levels by 6 to 9 meters, 19 to 30 feet, during the last interglacial period. For those unfamiliar with interglacial periods, they're the warmer interludes between ice ages, and this one provides a real-world example of how ocean currents can amplify climate effects, melting ice and flooding coastlines in ways that reshape continents. Now, here's the twist that could fuel endless debates. If the ACC has behaved this way in past warm epochs driven by natural orbital changes, could climate change from human activities like burning fossil fuels and deforestation trigger a similar upheaval now, but with modern twists? Some evidence suggests the current is already picking up speed due to global warming, which might seem to align with past patterns. But the new research models propose something counterintuitive. The ACC could actually drift northward in response to warming, opposing an expected southward pull from rising temperatures. This potential northward shift adds a layer of uncertainty, as it might counteract some warming effects locally but could disrupt ecosystems elsewhere. It's controversial because it challenges the straightforward narrative of warming makes everything worse. Instead, it hints at complex feedback loops where currents act like climate regulators, potentially buffering or exacerbating changes depending on their position. Most people overlook this nuance, assuming ocean shifts are purely negative. But what if a northward move helped delay ice melt in Antarctica while stressing marine life in other regions? The implications for global ecosystems, coastal communities, and climate systems could be profound, creating ripple effects that touch everything from fisheries to weather patterns worldwide. Published in the esteemed journal Nature Communications, this study underscores why monitoring the ACC is crucial as we navigate a warming world. For instance, imagine how nutrient-rich waters redistributed by a shifting current could boost productivity in some ocean areas, great for plankton and fish populations, while starving others, leading to dead zones and biodiversity loss. Or consider the carbon cycle. A faster, relocated ACC might sequester more CO2 in the deep ocean, helping combat climate change. But it could also release stored carbon, worsening greenhouse effects. These are the kinds of trade-offs that make this topic ripe for discussion. Do we view such shifts as nature's way of adapting, or as a warning siren that demands immediate action? What do you think? Is the potential shift of the ACC a natural phenomenon we should embrace as part of Earth's cycles, or a red flag signaling that human influence is pushing our planet toward unpredictable chaos? Do you believe scientific models can accurately predict these changes, or are there too many variables at play? Share your thoughts in the comments below. Let's debate whether this is an opportunity for innovation in climate adaptation or a call to radically curb emissions to stabilize our oceans. Your perspective could spark new insights for everyone.